Hi guys, here is another short lecture that isn't associated with any particular assignment, but it's information that we need to know. Particularly, we are talking about color systems, and these are also called color spaces, and these are just different ways of understanding how color exists and interrelates. A visual mapping of color in space. So some of these we'll see take the idea of color and a color wheel and expand it into the globe shape that we've seen a few examples of before. A few systems we'll look at. Chevreul, we've mentioned him quite a bit. Munsell, Itten, we've mentioned before. Ostwald, and CIE Lab, which is a lot more contemporary color space. Spectrum. This, you should know. Hue is the name we give of a parent color. Chroma is its saturation or intensity, which can be affected by tinting, toning, and shading. And tinting and toning and shading affect value, but they don't change the hue. They don't change the parent color. Hue, value, and chroma are those three components of color. This, again, tint is when white is added, tone is when gray is added, and shade is when black is added. Let's look at a few. So we know Newton's color wheel, and we know our color wheel derived from Newton. And we've looked at the expansion of that a little bit when we looked at Chevreul before, and I just want to talk about him again because of how important his work was. Um, he postulated that there are these natural complements. And yet another thing we've talked about are these opposites from each other. Doing that by considering after image, that's the color your eyes see after you see one color and you look away. And he also identified the 7 contrasts that we talked about way back when. The contrasts of hue, saturation, value, temperature, size, simultaneous contrast, and complementary contrast. So we know that visual complements are the result of after image. So those are additive, light-based. Mixing complements are when the actual colors are displayed, subtractive. And our examples of blue and yellow being optical or visual complements, and blue and orange being visual complements. So here's an example of an image you may have seen before, or one like this, where you stare at this for a minute and then look away at a white wall, and you'll see this in the correct colors it should be, which are red, white, and blue, which are optical opposites of these colors. His color wheel, just because it's so awesome. We're seeing that again. UFO break. So I want to look at Munsell now. All the other color systems and color wheels we've looked at are really the artistic interpretations of color aided by science. So Munsell wanted to re-inject science into color naming and came up with his own system in 1915, based again on hue, value, and chroma. Chroma is another word for intensity, um, created by Munsell. And it's actually used today in forensics and soil research and all sorts of pursuits. Um, for example, when you choose a color of paint on a swatch from the hardware store, and you give it to the person at the counter, they put it in to the computer, and the computer calculates the color based on the numbers ascribed to the hue or the value or the chroma. So his space might look something like this. You can see down here, we've got this blue that is being identified. So you can see here, this is the hue circle. So if we imagine a color wheel coming out around here, this is identified as blue, say blue 5 or something, and blue 4 would be here. and blue violet would be here, and blue violet 7 would be over here. So we'll see a mapping of those numbers later. But you might say, here's blue 5. It is a level 12 in chroma intensity, and it's got a brightness of 5. So you've got numbers ascribed to each specific color that you're looking at. And if we expand this and map it all out, it makes this really cool image. And this would be the 3D version of what he conceptualized. And what's going on here is this idea he had that certain colors could reach certain levels of saturation or chroma or intensity that other colors couldn't reach. So he postulated that a red could reach a higher intensity than something like a blue-green. So this is interesting. I'm not sure how much weight I give to this idea, but nonetheless interesting. I certainly think that some of these yellows could hit as much intensity as the red, but this is his system. And the positioning of the colors here is a little different than the colors on our color wheel, because these colors are based on the optical complements rather than the subtractive complements we have on our color wheels. So here's what his wheel looks like flattened out. These are those numbers that he gives to each hue. So this would be the position on the wheel, and then brightness coming up through this axis here towards us, and then intensity level coming out from the middle out to the very edge. And you guys know all this. So if you take out one of your tubes of paint, you'll see down at the bottom of the tube on the front, it says HSB, I believe, which is hue, saturation, and brightness. So another word for value. And it's interesting, our tubes of paint are actually labeled with the Munsell system. The no box, those process color paints that we put away, the ones that said primary cyan, primary yellow, and magenta, they're labeled like this. And here's an interesting thing. Here's white and black. And look, white is only labeled at 9.5, and the brightness scale goes up to 10. So the paint pigment is not a perfect white. Now this is a very idealized 10-step value scale here. They've actually extended this to 30-some steps now. Just so there's more increments. But we know from the millions and millions of rods in our eyes that there are far more grays and levels of brightness that our eyes can detect. Look at this black paint is a 1.8, so it's not even down at the very bottom. It's actually a little brighter than true black. Here's his globe from the side. And then here's a chart of all of these different colors, these different hues, and their amount of available intensity. So you can see there's a large amount of intensity in this magenta, and a lower range of intensity in the blue-green, like we pointed out before. Looking at someone else, Ostwald, who was a little more interested in finding harmony in color, and a little bit more artistically inclined than Munsell. So happening at the same time as Munsell. But again, this is a little more aesthetic than Munsell. Here's his color wheel, comprised of 30 hues. And if we take his color wheel and expand it into a globe, we get this super awesome object. And I actually used to make my classes do one of these charts in paint. But you guys have already done each of these things. You've done a grayscale, you've done tone, and you will have done tinting as well. So what you're seeing with this wedge is one slice or leaf of this globe. So he's got luminance. So this would be black down here going up to white. And then the tinting going from white here up to the full saturation color. And then the shading going from full saturation to black. And then all in between these tones are filled in like this. Here's a full cross section. And we can see this is interesting. Ostwald's globe really makes sense as a more stepped version of what Rung was doing with his globe very early on. I just think these are so cool. I can't imagine how much work it would be to create one of these, but it'd be such an awesome thing to have. It was actually hard to find images of these on the internet. I think there were so few produced. So much work would be involved to produce one. Okay, Itten. And I mentioned him before when we looked at color wheels, but the thing I wanted to get at with his system, and you've seen his star before, um, the reason this is developed this way, and it's got this little spinner on this. This is a plaque. It's a board, like a board game spinner. It has this little spinner that sits on top of this, and then at different geometric points, which you guys will learn about in the color harmony lecture, it tells you color harmonious schemes that you can put together. Um, Here's his version of what Rung was doing. And he was really interested in finding universal meaning and harmony and color. He ascribed specific shapes as naturally fitting with specific colors. So red naturally fitting with a square, and orange naturally fitting with this I don't know, quadrilangular object, yellow fitting with a triangle. And he doesn't really back this up with science, um, but he and a colleague, Kandinsky, put this survey to their painting students, and the majority of them agreed that these colors naturally went with these shapes. And we got to take that with a grain of salt, because they were all their students, and so they were already exposed to their ideas. Nonetheless, it's kind of interesting. Really interesting thing about Itten was his ascription of specific meanings to specific colors. And it's a very Western, sort of Christian centric um, take on color, but nonetheless really fascinating. So he puts yellow as bright knowledge and violet as dark emotional piety. Um, so if we mix them together, for example, red being material force and yellow being bright knowledge equaling orange, so that's power and knowledge equaling proud self-respect. Um, just really interesting stuff. If you want to look this up more, you certainly should. The root of a lot of the ideas of specific color meanings. And I just mentioned that because I also noted before that we aren't looking at specific color meanings because it is so culturally specific. There aren't really any exact meanings of colors that mean the same thing from one person to another person across the globe. We can say things like red feels very intense and it's an activating color, but we can't give it any symbolic meaning that is truly universal. Albers. Now, Albers, I mentioned in another supplementary lecture when we looked at simultaneous contrast and complementary contrast. He played a lot with the effects, the relative effects of one color upon another. And so up here, we've got these three backgrounds, and on top of them is all actually the exact same color. But by being on these backgrounds, it makes it look like these are three different colors. Here's the inverse of that. Um, these are different colors from one another, but by being on these particular backgrounds, they're made to look like they're the same color. And a little bit about what's happening is what I noted in that lecture. The toned or shaded red on top of these two backgrounds is sapped away, its intensity is sucked away on the full intensity red, whereas on the green, its complement, the intensity seems reinforced. So this looks darker and less red, but over here it seems brighter and more red. And you can read through all of this if you want a more detailed explanation of that. Here's what we've looked at. I want to take an aside and go um, a little bit nearer to contemporary. And I want to look at this. And we're stepping more back into the science side of things. These are available gamuts in digital displays. And so what you've got here, this is the full range of available light that humans can see. And these are the different gamuts that digital displays have. It's a few of them. And you can see how each gamut has its own limitations. And what's interesting to me, the type of display, the wide gamut RGB, that is able to capture the most of the colors that our eyes can see, still can't get over into this part of the spectrum. Really interesting to me, that this shows that our screens aren't anywhere near perfect yet. Here's an idea called black body radiation. Um, this is when the temperature in an object determines the color that we see. And it's best to think about this in the context of somewhere like space. So this is different than reflected color. This isn't with paint. This is with an object, a theoretically pure object in space has a specific temperature, thus it will give off light at a specific color. And and you can see right here is where our sun sits at about 5,500 degrees Kelvin. And I think it's actually 5,700 degrees Kelvin. Um, our sun sits right here, and that's why it is the color that it is. All right, lab color space. So this is an attempt to take the available spectrum laid out here and map it in such a way that is not artistic, but is exactly the way that the human eye sees. And I need to mention again, this is all theoretical, and this all happens within a digital device. So again, this is not perfect either. Um, what this is used for is sort of a global color system. So if I take a picture with my phone and I upload that picture into a computer and then I want to print it, one of the ways that can be done is that the data from that file is uploaded and the computer reads that within lab space and then is able to translate that into whatever sort of space the printer needs to use. So it's meant to be a global digital space, but it has probably the most beautiful conceptualization. Really cool. Um, and and you've got red, green, and blue as the subtractive primaries, and hue, saturation, and brightness, which is what you're used to. So RGB is different than what you're used to. This is a bit, I'm going to have to check back into this because this operates in an additive way. Um, Additive light, the way that light comes into our eyeballs is really strange. Um, if you combine red and green additively, you get yellow, and that still just doesn't make any sense to me. But that's the way it is. If you do it with theater lights, it works. A red light and a green light making a yellow light. The other combinations are far more logical. You know, red and blue making violet, for example. But red and green making yellow seems crazy to me. Um, Anyhow, after that aside, here's that space again. And here it is viewed from the top. This is just a really cool shape, I think. So the axes here are luminance, the red-green location, so that's across this axis. So here's luminance, just like we're used to from darkness to brightness. Here is the green to red, or red to green axis. And then here's the blue to yellow location. So within that, you could derive numbers and get to a specific color. That is it. Again, this is all just for your knowledge, and I will see you in the next video.